Hello everyone and welcome back to another calculus video. In this video we're going to talk about arc length of a curve and then we're going to talk about surface area of the curve. So let's say we have a nice smooth curve, and I'm going to start with some theory. So let's say we have a nice smooth curve. I'll call it f of x. We could talk about points on f of x, and we could divide it into pieces. And we could talk about how can we estimate the arc length for each of those. And that's why we're dividing this into pieces. So if I'm looking at the arc length here, a nice straight line would be a decent representation. And the smaller that my increments are here, the more accurate it would be. So we're heading towards finding an infinite number of little line segments here, which means we're going to end up integrating later. Well, let's talk about the theory of where this formula is going to come from. So I'm dividing this into pieces. Now this would be an okay representation of that arc, but you could see this would be a really good representation in that piece. So we're going to have to talk about that distance here, and we could talk about that distance here. And I could think about these things in terms of triangles, which means I could estimate that side, which would estimate that arc length using the Pythagorean theorem. And so that's what's going to happen here. So if I were to zoom in on that section, that first section that we were talking about here, between these two x values, this distance, we could call it delta x, and the distance in the y's, we could call it delta y. So by let me try again. The Pythagorean theorem would be delta x squared plus delta y squared would give us that length squared. And if I take the square root of that, I'll figure out what that hypotenuse would be. If we think about factoring out a delta x here, and that's what they've done in that second part of that theorem right here, or the explanation. So if we were to factor out a delta x, I'll do that up here. We're going to have the square root. We would have a delta x quantity squared. And if I factor that out, that's going to leave me with a 1 from this plus, and we're going to have delta y sub I over delta x quantity squared. And then if I take that piece out, the square root of delta x squared would just be delta x. That'll give us that square root of 1 plus delta y sub I over delta x quantity squared. And for small enough increments, this guy can be approximated using a differential, which is using the idea of a tangent line here. So my arc length is going to become the sum of all of these tiny line segments in here. So if I go back to my drawing, we took this picture from here to here and divided it into 5 different segments. Well, imagine if we divide it into 500, how accurate that would be. But that process gets tedious by hand. That's where integration comes in. So our formula for integrating to find the arc length of a curve, we're going to integrate from a to b, whatever bounds we're going to have. And it's going to be the square root of 1 plus f prime of x quantity squared, and that's we're going to integrate with respect to x. Now we could do this with respect to y too. It would just change that formula a little bit. And I'm going to use S for arc length, and when I write things on our notes, we're going to use a cursive S. So let's look at a few examples where we find the arc length of a curve. Let's say we have the function y equals 1/3 x squared minus 2 to the 3/2. We want to know the arc length from x equals 3 to x equals 5. So I'm going to start by drawing a picture so you can see what's going on. So I've graphed our function here, 1/3 x squared minus 2 to the 3/2. So that's that red function. I notice there's some discontinuities in here. We're only concerned about the part between x equals 3 and x equals 5. So you can see x equals 3 here. And then if I shift this up, x is going to be equal to 5 up here. We want to figure out what is that arc length. So the distance formula wouldn't quite cut it for us because this is not a straight line. It's a curve. It's hard to see the curve on this picture because of the scale. So let's use our formula to help us figure this out. So we know what our formula says. So surface area, and I'm going to use a cursive S for that. We're going to integrate from a to b, and it's the square root of 1 plus f prime of x squared dx. Go back up here and make sure I copied everything right. So we've got to figure out bounds. So I need to know, well, actually they gave us the bounds here. X equals 3 to x equals 5. I need to know f prime of x. So to find that derivative, it's going to be a chain rule. I'm going to keep that 1/3. I'm going to bring the exponent down. I'm going to subtract 1 from the exponent, and I'm taking the derivative of the inside. If you need to write out that process, that 5-step process to find the derivative, that's fine. You can do that. So now if I multiply 1/3 times 3/2 times 2, then 1/3 and 3 is going to cancel, and that 1/2 is going to cancel with that 2. So I'm going to have x times x squared minus 2 to the 1/2. So let's substitute in everything we know. We're integrating from 3 to 5. This is the square root of 1 plus the derivative squared. And then I need to simplify this so I can take the derivative. So if I square a product, that's the same thing as squaring each piece. And when I square that square root, I'm going to be left with just that radicand, x squared minus 2. So this is going to be 1 plus x to the 4th minus 2x squared dx. Let's see if we can figure out how to integrate that. I'm going to rewrite this as x to the 4th minus 2x squared plus 1. That guy factors into x squared minus 1 times x squared minus 1, which is x squared minus 1 quantity squared. And if I square a square root, again, I'm left with just that radicand, x squared minus 1. And then now let's integrate. So we're going to have x cubed over 3 minus x. We're going to go from 3 to 5. So I'm going to have 5 cubed over 3 minus 5 minus 3 cubed over 3 minus 3. So let's see, 5 cubed is 125. 3 cubed is 27. Don't forget to distribute that negative. So we have 125 minus 27 when I put those fractions together, which is what, 98 over 3 minus 2. So 98 over 3 minus 6 over 3 is going to give us a 92 over 3. So our arc length, the length of that segment would be 92/3 units. Let's look at another example. Let's say we want to find the arc length. We're looking at x equals 2y to the 3/2 from y equals 0 to y equals 4. So we're going to start by graphing this in Desmos. So here's my graph, x equals 2y to the 3/2. So there's our purple graph, and we're bounded by y equals 0 to y equals 4. So everything's in terms of y. So let's integrate this in terms of y. We're looking for the arc length of this piece of the graph, and it is a slight curve there. So arc length is going to work the same way. But now we've got to think about things in terms of y, but the process is still going to be the same. So we know our bounds are y equals 0 and y equals 4. They were given to us in the problem. We need to find the derivative. So we'll call this g prime of y. So if x equals to y to the 3/2, then the derivative, well, let me call this gy. Then our derivative, g prime of y, I'm taking the derivative, bringing that exponent down, subtracting 1 from the exponent. That 2 and that 1/2 is going to reduce, so I'm going to get 3y to the 1/2, or 3 square root of y. So when I substitute in everything I know, I'm integrating from 0 to 4. This is the square root of 1 plus 3y to the 1/2 quantity squared. And we need to square that. This is the square root of 1 plus 9y. When I distribute that squared, 3 squared is 9. Y to the 1/2 squared would be y. And this is going to require a u substitution to help us integrate. So I'm going to go ahead and just perform the integration here. We know u would be our inside function, 1 plus 9y. So du would be 9 dy. I need a 9 here, compensate with a 1/9 outside. So I would add 1 to that exponent. My new exponent is 3/2, and then I would divide by the new exponent, which is the same thing as multiplying by 2/3. So now I've got 2 over 27 times 1 plus 9y to the 3/2, and I need to evaluate from 0 to 4. I'm going to keep that 2 over 27 out. So when I plug in the 4, I'm going to get 1 plus 9 times 4. So that's 37 to the 3/2 minus, and when I plug 0 in, I'm going to have 1 plus 0 to the 3/2, which is 1 to the 3/2. I have 2 over 27 times 37 to the 3/2 minus 1. So that is my exact answer. Now, if I want to approximate that, of course, I could plug that in the calculator. And when I did that, I got 16.5972, which is the decimal approximation.